If you're a fan of astronomy, and I know you are, then you're probably familiar with the supernova remnant. This is this beautiful glowing blob of hot gas and dust that is left over when a star that is much more massive than the sun detonates, and it leaves behind this debris. Famous examples, the Crab Nebula, the Veil Nebula, Supernova 1987A. These are all different stages of what happens with a supernova remnant. But generally, the process is the same. The star explodes, it can outshine the rest of its galaxy for a little while, and then it fades away over the weeks and months. And eventually, when you get to the years, the actual bright part of the supernova is gone. You're left with the remnant. But a team of astronomers have found this very strange thing, which is that there are these supernova remnants which are old. They happened a long time ago, and yet they are still changing in brightness, sometimes by a factor of 100. Imagine if you were observing the Crab Nebula one day, and then a few weeks later you observed it again, and now it's 100 times as bright. We do not see that in our telescopes, and yet this is exactly what astronomers are seeing. And what is causing this bizarre behavior? So my guest today is Dr. Roy Kilgard. He's a professor of the practice in astronomy at Wesleyan University. And he is part of the team that has been using the Chandra X-ray Observatory to observe these strange pulsating supernova remnants. Now, I talked with Roy about this discovery and the underlying mechanism. Give you a hint, it probably has something to do with black holes, and how this sort of influences other kinds of observations that are out there. And so I think you'll find this one story very interesting, but the sort of the wider conversation that we have is also very interesting. So enjoy this interview with Dr. Roy Kilgard. Roy, you were examining the galaxy M83 with the Chandra Space Telescope, and you discovered something strange going on with some supernovae there. What did you find?
Yeah, so supernovae, I think probably most people who are watching this will know, are the remnants of dead stars. They've exploded. And the remnants that are left behind are, they're exciting objects, but they're not necessarily dynamic objects. They tend to not change on very short timescales. They tend to gradually fade on the timescale of decades to centuries. And when we were looking at these X-ray observations of supernovas in M83, we found a number of them that are variable in their brightness. On timescales ranging from sort of within a single Chandra observation of hours to many years spanning between observations.
And give people a sense of like, what is the normal bog standard supernova behavior that people would expect?
For these types of observations, people would expect for them to be faint, sort of lower energy in their X-ray emission, and very boring. They shouldn't change at all. We should be able to observe them from the beginning of X-ray astronomy in the 1970s all the way to the present day, and they basically shouldn't change on that timescale.
But you get this like instant brightening when the star explodes. That where it's, it can outshine the rest of the galaxy combined, or they're bright,
right? And they'll do that for weeks, and then they fade away to kind of obscurity. And there could be other things going on inside them. And we see things in the Milky Way, like the pulsar inside the Crab Nebula, which is a very dynamic object, but it's also much less luminous than these things that we're seeing in other galaxies.
But in the range that you see is a few weeks here or there, maybe a couple of months if it's a little stranger. But in general, you're going to get this very standard light curve coming out of this supernova.
That's right.
These supernova over a range. So they're extremely bright, and then they fade away over the next weeks and months, and then they're hard to spot unless they're relatively close, which hasn't happened since 1987.
Right.
Yeah. Okay. So then how did these objects that you were observing differ from what is the sort of standard playbook?
Yeah. So we ran tests of variability on all of the sources, all of the X-ray sources in M83, and then we cross-correlate them with catalogs of other types of objects, and that's how these showed up as being flagged as supernova remnants that were identified with optical and radio telescopes. And they immediately showed up as having a 100% probability of variability. And so that struck us as odd, and we dove into them further to try to figure out what they were. And that was sort of a 2-year-long rabbit hole that we went down.
Right. And give me a sense of how much variability. So, I've got a small telescope and I have observed, say, the Veil Nebula, and there are a few other supernova remnants. You can look at the Crab Nebula is a great example. I don't see variation, right? I see the same thing that people saw 50 years ago, and probably it looks different from how it looked 1,000 years ago, but it is not definitely fading away. Sorry, it is not sort of increasing in brightness again. So how much variability? If I was like pointing my telescope at the Crab Nebula over the course of some series of nights, how different would the brightness be?
For the most extreme ones, it's sort of a factor of 100 in brightness.
So I would look at the Crab Nebula one night. Yeah. I'd look at the Crab Nebula one night, and it's faint and there it is. And I do a long exposure, and then another while I do it, but now it's 100 times as bright, and it is like the brightest thing in the sky. Yeah. That's amazing.
Most of them
over what kind of time period will it make this oscillation?
Most of them, it's more like a factor of 10, but some of them are pretty extreme. That's still a lot. And, it varies from source to source. Some of them are kind of flickering within their observations on timescales of, I guess, hours is the time resolution we're sensitive to in those observations. And then with the rest of them, we don't really know. We're subject to the frequency with which they were observed with the telescope, which is somewhat arbitrary. This wasn't like a routine monitoring program of the galaxy. So we have observations that span a decade and a half or so, but a bunch of them are lumped together and then there are big gaps between them. So anything from hours to years. But we don't have a good probe of all the different timescales in between that to say.
Right. And again, going back to the images that I'm taking of the Crab Nebula, am I seeing it brighten in the core, or is the whole thing just getting brighter and fainter?
At these distances, we don't have the spatial resolution to tell that. The whole thing looks like a point source, but it, of course, isn't. If the supernova remnant, at least, is not a point source at these distances. M83's like 12 million light years away, 13 million light years away. So we don't have great spatial resolution. A single pixel in the camera is like tens of light years across. So there's not a lot of resolution out there.
And do we have any sense of their age?
I think there was one of them in M83 that was associated with a historical supernova that was in the 1950s. None of the rest of them are associated with historical supernovae, but we've only been really identifying supernovas in other galaxies for about a century. So older than a century, but the X-ray bright lifetimes of supernova remnants is at hundreds of years probably at that distance. So sometime in the last few hundred years is the best guess, which is not very long astronomically speaking.
Right. And so, speaking of best guesses, what do you think's going on?
Yeah, so we have kind of two thoughts for things that could explain this type of variability. And one is the idea of fallback accretion, which would be material that was blown off of the star in the supernova explosion, falling back onto the compact remnant, the former core of the star that's now either a neutron star or a black hole. And so it can kind of fall back and form a disk of material around the compact object that would then accrete onto it. That is possible. And that would happen relatively fast. That fits the timescales very well. We don't have great examples of that process locally happening that we know of. And so that's sort of more conceptual than practical unless we can find a good local analog of such a system. There are some things, but they don't quite match the observational properties of this thing. But that's a reasonable possibility that fits the age of the systems well.
And sorry, so would this be like a one-time event? Like I'm imagining sort of the supernova goes off. You've got all of the material that was maybe shed by the star before it actually detonated as a supernova. And then this new shockwave goes through that and heats it up and you get more brightness. But then is it all just falling back into the center in kind of blobs and chunks? Or is it sort of like this, it expands and then it all comes down together at once? Would we expect this variability to fade away in, I don't know, a couple of years when the infalling is complete?
So the infall could form a stable disk of material around the compact object. There will be some built-in rotation, even if it's slight, in the initial ejecta from the supernova, and that will kind of retain its angular momentum as it comes back down, and that will form a spinning disk. But you're correct. You don't have a resupply, so that will eventually run out.
But you've got like some kind of accretion disk that is just
But that could give us a reasonable kind of decades long lifespan for these things, decades to centuries kind of lifespan. And so that fits the timescale okay. It doesn't really fit the dynamic changes very well, though. And so the other possibility, and the one we currently favor, is that there is a baby X-ray binary in the system where you have the compact remnant of the dead star and a still living star in a binary orbit with one another. And the supernova was not so violent that you kind of blew the binary apart. And then the compact object can kind of siphon material from its still living companion star and form an accretion disk around it. And that fits the dynamics. X-ray binaries are very common in galaxies. We have, 100 or so very luminous X-ray binaries in our own Milky Way. When we look at other nearby galaxies, we see about the same number based on the stellar mass and star formation rate in those galaxies. And so that fits the dynamics of these systems very well. It doesn't fit the timescale very well. We think the timescale for forming an X-ray binary after the supernova explosion is longer than the X-ray luminous lifetime of the supernova remnant that we think we see these things embedded in. So that's mysterious. Either these are really rare examples of fallback accretion that we don't see locally, or they're a much more common type of object, but that's formed faster than we think they should form dynamically after the supernova explosion. Well, there are more possibilities, but those are kind of the two leading ones.
Right. Yeah. I mean, like I'm thinking about, say, I don't know, Cygnus X1, right, which was like the first black hole that was ever really discovered, and that's a classic X-ray binary where you've got this black hole and the star is going around. The only way you know about the black hole is just because of this material that it is feeding on. So what, when you think about something like, say, that, what is the length of time? Like, you're saying that process takes a long time for that feeding to begin, long after the supernova remnant has kind of cleared out and faded away to the back, blown away by the interstellar winds.
Yeah, that's right. So if the objects are too close together, then when the supernova happens, you will disrupt the binary probably. And so the companion star is no longer a companion, but one of the things will get kicked out of the system, or both, and you don't have a binary anymore. So you need them to be a little farther apart to form the binary in the first place. But gravity is very stable, and if neither one of these things is losing mass or losing momentum, then they're going to stay the same distance they are apart from one another for a really long period of time, unless something changes. And the thing that can change is the other star can evolve. It can lose mass as it's aging, or it can be close enough that it is losing material to the compact object. It's very hard to find theorists who are willing to place really good constraints on how quickly that process happens of those objects coming together that closely, because it's a very complicated problem to solve. But estimates are kind of in the tens to hundreds of thousands of years timescale, which is, again, astronomically short, and it's shorter than the lifetimes of the stars by quite a bit, but much longer than the supernova remnant will stay visible to us before it fades away into obscurity.
It does mildly overlap. I mean, I think about, that example I gave earlier, right? You've got the Crab Nebula. It's around 1,000 years old. We've got Tycho supernova. We've got the 1987 one, so we can see what different supernova are. And I think about some of these really old ones, like the Veil Nebula. It is on the order of many thousands of years old, and it is very large and diffuse and fading away. And only with a long exposure on your telescope do you even get it. That sort of sets that upper boundary, right? Like 10,000 years, and these things are hard to spot at that point.
That's right.
Yeah, but this, you're saying, no, we're looking at, say, 10 times as long for these things to finally get into a place where you can start to get that accretion going off. Okay, so you've ruled out your two ideas. What do you got left? Come on, I want to hear the crazy one that happens to
So I don't think we've ruled out either of those ideas. I think they're both viable, but have some challenges with them. I think the most out there idea that's not sort of breaking physics in any way is that maybe the things that look like supernova remnants aren't supernova remnants. Maybe the X-ray source is one of these compact objects. It is an X-ray binary, but instead the X-ray binary is accreting a lot of material and producing jets the way kind of supermassive black holes often do. And those jets are interacting with the material in interstellar space around them and sort of blowing a bubble around the object. And this isn't crazy. We have a couple of examples of these in the Milky Way. The most famous one is an object called SS433, probably. And even SIG X1 that you mentioned, it doesn't quite have a bubble around it, but it does have a shocked nebula around it that you can see in certain wavelengths of light. You wouldn't see it in a nearby galaxy, but there are examples that where you certainly would. So that is a possibility. I think there are a couple of problems with that. One is that I guess the people who made the catalogs of supernova remnants might not be too happy about me telling them a bunch of their supernova remnants are not that. But also, there are a lot of these things in M83, and that would be somewhat surprising to find a large number of these kind of X-ray binaries blowing bubbles around themselves in a single galaxy. But it's allowed. We have examples of them.
Is there anything special about M83? Is it a starburst galaxy or
M83? So that's a great question. M83 has it's a very high star formation rate galaxy. It has a really intense star forming region in its nucleus. So its global star formation rate isn't actually all that high, but where it's forming stars, it's doing it very, very intensely. But this was actually the first question we asked ourselves: is M83 unique? And the answer is no, it's not. One of my former students, summer student, Zoe Hoyland, who's not a co-author on this paper, but is writing the follow-up paper right now, looked at these in the galaxy M51, which is the Whirlpool galaxy. It's a canonical example of a nearby interacting galaxy, and it is very high star formation rate. If you kind of scale it for stellar mass compared with the Milky Way, its star formation rate is close to 100 times what ours is, scaled, kind of pound for pound. And so we look for these things in M51, which also has a really nice catalog of supernova remnants produced by many of the same people who made the catalog in M83. And it also has a bunch of them. There's about 24 of them in M83, and there's about 24 of them in M51 as well. And so it seems like just from that piece that there's some correlation with star formation, which makes sense because supernovas are correlated with star formation as well. You get them from high mass stars that live for these brief moments of time. And so we also looked at M101, which is another nearby galaxy, but has a much lower star formation rate and also a good catalog of supernova remnants. And it has 0 to 1 of these things. It has one, but it's not a great example. It's variable-ish, but kind of right on the edge of you could maybe dismiss its variability as a statistical fluke. It's not a high significance detection of variability. So that's kind of where we were at the time of when we had our press release about this. And over the last few weeks, I've had one of my undergraduate students looking at kind of everything that's been observed with Chandra over the last couple of decades. And there aren't as many galaxies that have been observed as many times to look for that nice long baseline of variability. But we've found a few more of these things in a handful of other galaxies. And we're kind of now starting to wrap our brains around what this means. And if we can say something more definitive, then it seems like they're associated with star formation, which is all we can currently say.
Right. But I mean, supernova are also associated with star formation. So, so having supernova remnants in places where there's actively star forming is not a surprise. What would you use something like Rubin to try and help you double check?
Oh,
because you've got this great survey that's coming out, every night they're finding loads and loads of new supernovae across the universe. Is there some pattern in there that you could compare with?
We would need to be able to do good X-ray follow-up of those supernovae that Rubin is detecting. And we don't currently have an X-ray telescope that can do that, because while Chandra is still a functioning X-ray telescope, thankfully, these objects are kind of at the very red end of the X-ray spectrum. They're the lowest energy X-ray objects. And over its lifetime, Chandra has been losing sensitivity in exactly the place where we need it most for these observations. So while it can still do amazing science for a whole suite of other stuff, for this very specific problem, it can't quite do it anymore. But that's okay, because we think the timescale for this is probably, we need the supernova to be done doing its business anyway, and for the system to settle down. So we need the timescale for follow-up to be at least a few years, if not more. So this is actually a project that's well primed for whatever the next big X-ray telescope we build is going to be, because that will probably be kind of a decade or more from now timescale. So it's an exciting prospect for the future. But not anything we can currently do with it other than start making our list and thinking about what we're going to do a decade or so from now.
Right. And hoping for that next generation X-ray telescope that was requested in the last decadal survey.
Yeah.
Or two decadal surveys ago, right? The links.
I'm cautiously optimistic, I would say.
Okay, good. I'd like to talk just about X-ray binaries in general as an object, because, my audience is quite fascinated with this idea, like this line between a neutron star and a black hole. Do you always know which one you're looking at? In some system, you're like, okay, that's obviously a neutron star, or that's obviously a black hole, or is it actually hard to tell?
It can be very hard to tell. And the only definitive way I guess there's kind of two definitive ways you can know. One is that you can measure the mass of the companion star very well, and then measure the properties of the binary orbit very well, such that you can use Newton's laws to figure out the mass of the thing that you can't see. And if it puts it comfortably into the acceptable mass range for neutron stars or black holes, then you know what it is. So you can measure it dynamically. That's one way. The other way is if you see variability from the object that is on a timescale that's so short that if it were happening in a black hole, it would be within the event horizon of the black hole, then that's impossible. And so the thing is a neutron star. So like millisecond pulsars can't ever be black holes, because the pulsation timescale that we see from those things would happen within the event horizon of a black hole if the thing was a black hole.
Right. Okay. That's interesting. But for a lot of the ones that are farther away, if they're not giving off that sort of regular radio waves, you kind of have to, and that's why you call them X-ray binaries. It's funny because you don't hear them as like binary neutron stars, binary black holes. It's this general classification.
Yeah, and we confuse the matter even further because we talk about them as being either low mass X-ray binaries or high mass X-ray binaries. But the mass in that case is the star. It's not the compact object, because the star is the thing you can see. So I know if it's a blue star, it's a high mass star. If it's a red star, it's a low mass star. It's a piece of cake, right? It's
right. But that has nothing to do with
nothing at
what
all.
is the compact
nothing
object.
At all.
Right.
You can have all combinations of things.
So one thing that's quite interesting to me is how astronomers are finding that these these compact objects, are very similar in behavior to the more supermassive versions. That you get very similar behavior on a micro quasar, a tiny black hole that's feeding on material. It produces jets. It has an accretion disk. It's sending off, as it feeds, it's sending out X-ray radiation in a way that is really directly applicable to the supermassive black holes. And I know you've been also doing a lot of work on supermassive black holes and active ones. Does it give you a kind of like a mini lab to study some of those ideas for the larger ones that are 6 billion light years away?
Yeah, welcome to my TED Talk.
Okay, I stumbled into your TED Talk.
This is one of the main questions I've been interested in for my whole career is what are the physical properties that scale across kind of 8 or 9 orders of magnitude in mass? And for some things, we see really direct correlation and things that scale beautifully well. And for others, we just don't know. And the problem is that you will often see similar behaviors in these things that are 10 solar masses versus 10 million solar masses. But we have scarce examples of things with masses in between to know that these things that we see that are similar are really kind of scaling across that whole mass range. So it would be lovely if we could find, a 10 solar mass black hole and then 100 solar mass black hole and then 1,000 solar mass black hole and all the way up that are otherwise identical and see what really scales across those mass changes.
And so which elements do seem like they scale?
There is a relation between the temperature of the disk of material around the black hole and its mass, and that scales beautifully across all of these orders of magnitude. It seems likely that what's causing the launching of the jets in the systems must also scale across these huge ranges in mass. But the physical scales involved are so much different that it's a little hard to understand how that works. So those are the obvious things. But the physical models that we use to model them are very similar otherwise. It's a disk of hot material, sometimes have some clumpy, cloudy other stuff around them and jets. And they're very, very physically similar.
And so you mentioned something that I've never heard before, this correlation between the mass of the black hole and the temperature coming from the region around it. Does that give you a way to estimate the mass of a black hole by measuring the temperature?
It does, assuming that the material extends all the way to the innermost stable orbit around the black hole. It doesn't have to. The material can be further out than that. But it will tend to fill into that most stable orbit unless something physically changes in the system that prevents it from doing that. So yeah, there is a direct correlation between that inner disk temperature and the mass of the compact object. So we can, in some systems, if we can place a very nice temperature constraint on that inner edge, place a limit on the mass of the black hole, but it's only a limit because the material could be farther out. But it's a lower limit for that reason. If a bigger black hole has material that's farther and farther away from it. So this is kind of a maybe counterintuitive thing, I suppose. But the more massive the black hole, the cooler the inner edge of the accretion disk because it's farther away.
Right. And I mean, isn't there a kind of, it depends on the direction the black hole is spinning and the direction that the accretion disk is spinning.
It does depend on those things too. That's true.
Yeah. And so you can get a different gap depending on those. And often I know you measure the direction the black hole is spinning by measuring the gap. And so,
yeah. And even measuring the black hole spin can be pretty hard when you get to these objects that are quite a bit farther away. We can for some, but not for a ton of them.
Yeah. I know astronomers are still arguing about the direction of even the supermassive black hole at the heart of the Milky Way. What's its inclination compared to us?
Yeah, for studying that black hole in more detail, it would be good if it were feeding more actively. That would not be good for any other reason, but it'd be great for studying it.
Right. Yeah. Your last research, your final research. So one thing that really fascinates my audience is this dividing line between neutron stars and black holes that, both are continuing to accrete material. And there is an upper limit to the mass that a neutron star can collect. Do we think, and space is big, we've seen plenty of things happen out there. Do we think we're seeing what happens when a neutron star collects more material than is sort of managed by the Pauli exclusion principle, that these things are going into some other form?
Yeah, I wonder if we would know if we saw it when it happened in an X-ray binary. I think we would need very, very good observations of a nearby one to know if we actually witnessed one cross that line, because I don't think it would be
like not a supernova. Like it wouldn't be dead obvious. It would be subtle.
I don't think so. I think it would be more subtle. I think it would depend on what observational properties, like what are the properties you have been able to observe from the thing while it's a neutron star. But there's so much we don't know about what's going on in the interior of neutron stars that it becomes a very difficult problem to solve. We don't know if neutron stars, further collapse and become quark stars, which has been one of the proposed things as a stage before a black hole. We don't know if that happens. We don't know if neutron stars are really these kind of 99% balls of neutrons that have thin crusts of normal material, or if it's more like the onion layer that we see in living stars, especially living high mass stars. We can have multiple different layers of material inside from different cycles of fusion. It could be that a similar thing goes on where the very beginning or the very center of the thing is some weird superfluid that's surrounded by a quark star layer, that's surrounded by a neutron layer, that's surrounded by another crust. We don't know. The way that people try to place constraints on this now is by measuring the radii of multiple neutron stars, because if it is kind of ball of neutrons all the way down, we can make a measurement of what the diameter ought to be based on its mass. And if it's smaller than that, then something else is going on in its interior. There's been this little telescope bolted to the space station for a decade or so now, called NICER, and its whole job in life has been to measure the radii of neutron stars and place constraints on this problem. And it hasn't answered the question fully yet, but it certainly is pointing to the solution being more complicated than ball of neutrons all the way down.
Right. Like, but it could be neutrons at the center, something that's more akin to a white dwarf on the surface, and maybe something more dense in the center, not clearly way too small, and so it has to be.
There have been none that have been way too small yet. Yeah, that's correct.
Yeah. Okay. But still, I mean, we sort of think about this tipping point for white dwarfs when they're pulling material off some companion star and then they detonate in an instant as a type 1a supernova. And you would think that a similar energetic event would happen with a neutron star, but it's interesting that it could be a more subtle shift.
Yeah, a neutron star is not much larger than what the event horizon of an equivalently massed black hole would be. And so if the sort of transition from compact object made of real stuff to black hole is instantaneous, there's not a lot of stuff that's outside the effective event horizon, if you will, that could get away. So I think you're not allowed to have too dynamic an explosion. But that's a bit outside my area of expertise, I think.
Right. Yeah. I mean, it's such a fascinating idea that you have this object that is already just defying our comprehension at the density of it, and then at some moment it just kind of goes, it sort of goes in one more notch.
Yeah.
And yet, and then eventually makes that final transition into a black hole as it continues to feed. But if you're saying you can't tell the difference between a neutron star and a black hole, then it does not surprise me that you can't tell the difference between a neutron star and something that's in between in a black hole. Like this is a tricky observation, and so more data needed. Oh well, Roy, what are you obsessed with right now?
Wow, we've touched on a lot of my obsessions, but I'll give you one that's related to the topic that you brought up about where this tipping point is between when something becomes a neutron star and a black hole. a question that I've been obsessed with for my entire professional career, but that continues to obsess me nonetheless, is what is the upper limit to the mass of a black hole that we can make from a single parent star? And we know that you form things like the black hole in Cygnus X1 from a single parent star. And we know that that thing is around 20 times the mass of our sun, which means the star was presumably quite a bit more massive than that before it died. But what's the upper mass limit to that? We don't really know what the upper mass limit to a star is, but we have kind of some constraints that we place on the modern universe. And we think when the universe was mostly hydrogen, you can make them a little more massive. So maybe in the early universe, you could make them a little bigger, but what is the upper mass limit? And the reason why I'm obsessed with this, I guess there's two reasons. One is that we still don't know how you form the supermassive black holes that are at the centers of galaxies. Although maybe we're starting to understand that picture a little bit better thanks to the James Webb Telescope. But also it gets back to that question of how physical phenomena scale over many orders of magnitude in mass. And the scarcity of examples of black holes that have masses in this in-between range. And when I was a baby scientist, I was fortunate enough to work on an object in the galaxy M82, which is our local starburst galaxy. And it's the brightest X-ray source in M82. And so it gets the clever name M82X1, because that's how we do. And when we first started looking at this thing 25 or so years ago, it looked like its mass is around 400 or 500 solar masses. And that's a weird range because we think we can't form that from a single parent star. And over 2.5 decades of observing nearby galaxies, we have 0 more good examples of objects in that mass range. And all of the other constraints we have on black holes that are approaching, but not quite at that mass range, come from gravitational wave observations, where we're starting to get up to a couple of hundred solar masses, but not too many examples. And so, how massive can you make a black hole from a single star sets the limits on black hole mergers that we see with gravitational wave telescopes, and it helps inform the scenarios for formation of supermassive black holes in the early universe. So that's the thing that I'm really obsessed with.
Do you have a sense of where you think this lies? Because I mean, I know what you mean about this idea of supermassive black holes. I mean, thanks to Webb, we are seeing these quite massive supermassive black holes early on in the universe, things that are approaching 1 billion solar masses within the first, say, billion years of the history of the universe. Who ordered that?
Right.
And so then and if you're just like saying, well, you had a star and it went supernova and then found another star and they merged and then another one and then another one, and it's also been feeding all this time, it doesn't get you to that kind of mass regime. And so now you got to go, well, maybe bigger stars make bigger black holes. What if one has 1,000 or 10,000 or 100,000 times the mass of the sun? Well, can you have a star that big? Apparently, probably not. So then can you have a direct collapse black hole? Can a black hole feed faster than we thought?
That's right. Those are exactly the questions. Yes. Can you form them through direct collapse? Can a star get to keep more of its mass when it dies than we think it ought to if it explodes as a supernova? And then how quickly can you grow them on reasonable timescales? And what constraints can we place on this in the local universe where they're much easier to study than the things that we're seeing with James Webb that are at the farthest reaches of the universe?
And like, obviously I've been obsessing about this question as well. Do you feel like an answer is coming?
I don't know. I think the question of direct collapse black holes, I think an answer to that question is coming thanks to observations with James Webb. And I'm thinking in particular about a thing I know that you've talked about before, little red dots. And
but there was another example that happened where some astronomers are claiming that they had seen essentially a region of a galaxy merger that was too dense and had to be the result of of a direct collapse black hole. And that was a couple of months back.
Yeah, there have been a handful of examples of possible direct collapse black holes. There have also been a couple of examples of high mass stars in relatively nearby galaxies that have disappeared without any obvious supernova remnant associated with them. And those are great examples of kind of the small scale potential direct collapse black holes. So we have compelling evidence that that's happening. And I think that's the direction where we'll see more progress in the very, very near future. I think we need an upgrade to the existing gravitational wave telescopes that is probably going to happen in the reasonable future to place constraints on it from the gravitational wave, the black hole merger side of things. And then on the observational side of things in the nearby universe, I think we need a next generation X-ray telescope to answer that question.
Right. But something like Vera Rubin, which just says, someone pours through Vera Rubin and says, show me all the stars that disappeared.
Yeah. You for sure will be able to place some interesting constraints on direct collapse. Will it tell you about black holes? I don't know, right? Because you're not necessarily going to see a neutron star in those cases either.
And it doesn't necessarily answer the question of can you have a star turn into a black hole, which is sort of a different question. Is can you have a cloud of gas with 1 billion times the mass of a star turn into a black hole?
That's right.
Different creature.
Yeah.
So, but maybe there's some common elements in there. Yeah, it's such a fascinating question because I think people were really hoping that Webb was just going to go like, here's your answer. And no, turns out it's the reality.
Turns out it made the problem worse.
Yes, which is in the end, that's what keeps astronomers.
That's right.
So I think that's all fine.
It's great. We get excited when there are questions that we don't know the answer to, and it's not just because that keeps us in business. It's because that's where our obsessions lie.
Yeah, exactly. Yeah. Well, it was a fascinating conversation, Roy. Thank you so much for taking the time to chat with me, and good luck with your research.
Thank you.
Well, I hope you enjoyed this interview with Dr. Roy Kilgard. As always, I went into more detail and on an additional topic with Roy, and this was about his fascination, his infuriation with light pollution, and he has been working very hard to tackle light pollution on the campus where he works, and really the city that he is in and the state that he is in, and that there are great reasons to reduce your light pollution, that you can save energy, that you can protect migrating species, that you can make a place that is more energy efficient and yet also brighter in the places that you need it. Point the lights at the ground, not up in the sky. And of course, that also helps out astronomers. And if you've ever been to a city like Tucson, where they take this very seriously, it is night and day, pardon the pun. And so Roy gives some real practical examples on how you can help fight this battle, both improving your own house and just get involved in your local community to try and reduce the amount of light pollution that's going on. I'm going to make this longer version of the interview available over on Patreon. As always, these longer editions are completely free. There's no ads. You can just go watch it right now. And to reward you, we've got that additional content. I'll put a link down in the show notes. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Carrot, Chuck Hawkins, Commander Bielak, Dirk Finga, David Gilton, and David Matz, Enthralled Reading and Math for Toddlers, Evan.Pro, James Clark, Jeremy Madden, Jim Burke, Marcel Smith, Mike Russell, NASA Ocean Guy, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Renkaidu, Richard Williams, Sean Sargent, Stephen Feinland-Munley, Team 49, Telescopes Canada, Vlad Zeppelin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. It's funny, this conversation, it wasn't really until the end where I think the real obsessions started to reveal themselves. And this is just this idea of how supermassive black holes get so massive so quickly. It's just like, it's absolutely an infuriating, beautiful, wonderful, crazy mystery that is just compounding year after year. That, we see the stellar mass black holes, we see the supermassive black holes. How does the supermassive black hole grow so quickly in relation to the galaxy that is around it? And it was hoped that James Webb would answer this question, that you would get to this place where you're like, okay, we can see the building blocks of these small galaxies that are coming together to form these larger galaxies. There is your answer. And that the supermassive black holes of the small galaxies are feeding in. But no, we've got galaxies with supermassive black holes that are a billion times the mass of the sun, seen early on in the history of the universe. And so whatever mechanism is going on, it is surprising and yet is an entirely new field of inquiry. And I think it's the message that you get is that the universe is not only weirder than we suppose, that it is weirder than we can suppose, to use the famous quote, and that the universe is not obligated to play by our rules. The universe does what it does, and that it's our job to just kick back, to trust in the process, to observe, to see what we see, and enjoy the satisfaction of the mysteries that unfold. And every time a new mystery comes along, you should be grateful, glad. There's more to learn, more to discover, and it should keep your curiosity going for the rest of our days. All right, we'll see you next time.